Cape Talk, the world of science with Dr. Chris Smith, the naked scientist.
Ooh, we are excited to chat to Dr. Chris Smith. Good morning, Chris. How are you this morning?
Well, I'm really good shape. How are you?
Fantastic. I understand you have hit our shores very safely. Welcome to South Africa.
I know it's great. And I know ostensibly it is summertime in the UK, but actually the
Yes.
weather here in Durban, as is classically the case in Durban, is fantastic and it's beautifully warm and it's like winter at home in comparison. So bring it on. I'm very pleased to be here.
Fantastic. Very excited as well. I'm not sure if you had landed by this time and might have had a spotting of this, but one of the questions we've received from a listener is, I saw the moon at sunrise, but I only saw half the moon. Why was it only a half moon?
Well, you have to think about where the moon is and what the Earth's doing in relation to the moon to understand the answer to this question. And that is that the moon orbits the Earth and it takes 28 days for the moon to go right round the Earth. But the Earth turns on its own axis inside the orbit of the moon, and it takes 24 hours to do that. So every day the moon makes a journey across the sky. So that's why you can see the moon in the first place. But
Yes.
remember that because the moon is going around the Earth, taking a month to do it, as it goes round at different stages of that orbit, different amounts of the moon's surface will be lit by the sun. Because when you see half a moon or a full moon, you're seeing the sun's light, which has gone past the Earth and reflected off the surface of the moon and come to us. And therefore, when the moon is facing or is directly between us and the sun, none of the surface we can see is illuminated by the sun. So we don't see any moon surface. So we call that a new moon. As the moon continues around on its orbit, a bigger and bigger patch of its surface is being illuminated by the sunlight. And therefore you see progressively more as the month goes on until you get to the full moon, which is where the moon is directly with the Earth in the middle of a sandwich, where you've got the sun on one side, Earth in the middle, moon on the other. So all of the sunlight is illuminating all of the moon surface that's facing us. So we see a full moon. And then it begins to wane again as it goes back towards being the new moon. And that's why you see a different amount of the moon surface at different stages of the lunar cycle.
Indeed. And we are in our waning phase here in Cape Town. Hassie in Grassy Park, good morning. You want to
Good morning.
know about graying?
I've got a question on hair again. My head has hair, my face has hair, my nose, my eyebrows, etc. But only the beard and the hair on my head goes silver grey. My eyebrows, my eyelashes, nose hairs, ear hairs are all pitch black.
Interesting.
Why? I tried to understand that.
Are you dyeing your eyebrows?
No.
It was a joke. It's fine.
In fact, the hair on the rest of my body, arms and legs, is all black. But my beard is silver. It's white, Snow White.
Now, there was a sketch by two comedians in the UK. It's about 20 years ago. And they dressed up as two Swedish gentlemen with nice blonde locks. And the joke was, they were saying, in Sweden, everyone asks us, why it is that our hair's blonde and our genital hair is dark. And they said the answer is very simple. We dye our pubes. But I'm sure that's not the case in your case. But the bottom line is that the hair has its colour because the hair is naturally a white colour because it is the protein keratin. And keratin is not coloured. It's a white material. Colour is added in the form of different amounts of the chemical melanin in different combinations, which are added to the hair as it forms in the hair follicle. And melanin comes in different flavours. There's one called eumelanin, which is black. And then there's pheomelanin, which is more yellowy red. And the different amounts or the different relative proportions that you add to the hair gives the hair a different colour. But this only happens for a certain period of time before, for some reason we don't really understand, those melanizing cells that add the colour to the hair stop working. And they don't do it everywhere all at once. They do it in patches. So certain parts of the body's surface will find the hair going grey, and in other places the hairs next door will still be having their full complement of melanin, so they look the normal colour. And this is why people say that they go grey or salt and pepper grey before they get white hair. Now, why it is that some bits of the body are more vulnerable to this happening sooner than others, we don't really know, but it's probably a reflection on the metabolic rate of the cells that are doing the melanisation in those areas, because some parts of the body grow hair faster, they turn over the hair faster, therefore they've probably got a higher metabolic rate. And if you've got a higher metabolic rate, you're probably burning yourself out faster. So we suspect that probably some parts of the body that's happening more than others, which is why you then lose your pigmenting cells and the hair reverts to its natural white colour in that part of the body.
Answer the question, Hassie?
I'm listening.
Fantastic.
Yeah.
Thanks for the
I still
question.
got black eyebrows and black eyelashes and silver beard.
Yeah,
Thank
well, we
you.
don't know
Thanks.
exactly why different bits of your body's surface extinguish the function of those melanizing cells before others. In some people, it's certainly random, but in other people, certainly there are vulnerabilities about certain parts of the anatomy where your hair will go, well, where the hair produced there will go grey sooner, but we don't know exactly why that is. But scientists suspect it's something to do with the metabolic rate of the tissue burning out the melanizing process sooner in those body areas.
Chris, can a coin falling from the top of the Empire State Building kill you?
Well, I did the calculations on this a few years ago because this was spawned by, there was some footage on television of people who were at the end of a coup or something, and the war was over, and they were firing guns up in the air. And so someone wrote in and said, the bullet that leaves the gun, how fast does that come down? Could that kill someone? And the physics is that if you fired a gun straight up in the air, the bullet leaves the gun with a certain amount of energy, which if you neglect the effects of air resistance, it's going to convert the kinetic energy, the speed of the bullet leaving the gun, into gravitational potential energy, because the bullet's rising and doing work against gravity. And so it's gaining altitude but slowing down. It will get to a point where all of the kinetic energy is turned into gravitational energy, and it will then begin to accelerate downwards again. Now, if there was no air resistance, then the bullet would end up coming down and reach a velocity the same as it left the gun at. So it would be perfectly capable of killing someone, except for the fact that the bullets don't come down nice and straight in a streamlined way, and they've got air in the way. So they do lose a bit of velocity on the way down, so that they do slow down appreciably. We then looked at the calculations for coins, because coins will actually tumble as they fall, and therefore they're going to have a lower terminal velocity than a streamlined bullet, but they nonetheless could be quite injurious. The conclusion I think we reached was it probably wouldn't kill someone, but it really would hurt, because it will quite quickly reach its terminal velocity, and then it will fall at that velocity until it stops, because it either hits the ground or hits something like a person's head. So yes, it's perfectly capable of causing injury, probably not capable of killing someone, though. That was our calculation. But if anyone has also done the calculations and knows differently, please do tell me.
Of course. Francois and Hart Bay, the Earth's murmur.
Hi, yes. I've heard about the Earth's murmur before, and then we were a couple of years ago, we were in the Tankwa-Karoo. We stayed on this farm. We were like 10 kilometers away from the farmhouse. And it was really like absolutely nothing. It's about 3 o'clock in the morning, I woke up with this magnetic resonance. And I thought it was like in my head, and then I went outside and it became louder, and there was nothing, but it was constant ringing, and it wasn't just inside my head, I could actually hear it. And I couldn't figure it out. And then I thought about the thing that I saw once, the Earth's murmur. And what is that about? And could you explain it for me? Or what is the scientific reasoning behind it?
I wonder if you're referring to a story, it was about 15 years ago, where they were saying the planet hums. Normally things hum because they don't know the words.
Yeah,
but in the case of the Earth humming, I think they were saying the natural resonant frequency of the Earth was at this particular amount. I'm not sure where that story originated. There's certainly vibrations that come in from space, because what we know happens is that the arrival of the solar wind and cosmic rays, they ricochet off of the Earth's magnetosphere, the magnetic shroud that surrounds the Earth and extends out into space. And as you get this acceleration and deceleration of particles in the Earth's magnetic field, it does cause a sort of oscillation. And that may be what they were referring to in that story. But I think the frequency that runs at is way different to the regime that your ears work at. So we wouldn't be sensitive to this as an acoustic phenomenon, I don't believe. Whether or not there's some other thing to account for your experience, there must be, because you wouldn't be hearing that for that effect I just described. But the other thing that people have documented in recent years is so-called infrasound. Our ears work down to about 50 hertz, 50 cycles per second, and below that you can't really hear the sounds 20 to 50 is going to be the threshold of human hearing. Below that, though, it doesn't mean you don't hear the sound. You can still be sensitive to the sound. And people have done experiments where they've gone to places that people describe as having a presence or being haunted or making them feel uneasy. And this includes old buildings, big old structures. Some natural geographies do this, and they recorded an above average amount of this infrasound, so sound waves at very low frequencies in those areas. And we're still sensitive to those vibrations because, especially in your abdomen, you have a lot of vibration sensors in the tissues that surround your intestines, which is probably where the old saying, my gut instinct, comes from. I feel it in my gut. And this is because we are very sensitive to vibration in that part of our body. And so when people go to somewhere that they describe as haunted or having a presence or there's a weird sensation, sometimes it can be because there is this infrasound. And it might be that the area you're in, the geography, perhaps the wind blowing over the terrain or the buildings nearby were being made to vibrate with this very low frequency that you couldn't physically hear, but you could sense it. And it might be that that's part of the phenomenon. And I think that's very different than the Earth having a natural hum, which I think is an electromagnetic effect caused by interactions between the magnetosphere and arriving cosmic radiation.
Cape Talk, the world of science with Dr. Chris Smith.
One of these says, why after nuclear disaster can effects from it continue for years, even decades after? Some children in Vietnam are born with defects and Chernobyl is perhaps not livable. Why is that?
Well, it's not entirely true that Chernobyl isn't livable. We actually answered this question on the Naked Scientists podcast this week, actually. Someone wrote in and said, why is there this enormous exclusion zone that's okay for animals and not for humans? Actually, there are areas of that exclusion zone that do have some high levels of radiation, but the average exposure there is really quite low. And so animal life and the people that refuse to leave is thriving there, actually. Most of the danger from things like radiation, though, is that some of these disasters produce fallout. And this nuclear fallout can include some very long-lived chemical species. By long-lived, I mean they're radioactively long-lived. When you have something that's radioactive, what's happening in that particular chemical is that the atoms have a nucleus, the structure at the core of the atom, which is unstable, and it doesn't hang around very easily, and it tends to break apart. And when it breaks apart, it releases energy, which can include forms of radiation. And that energy is sufficient to damage the DNA of your cells and my cells, anyone who gets in the way of it. And if you damage DNA, you're at risk of getting things like cancer. So one of the risks of a nuclear disaster or a nuclear bomb, and even from too much sun exposure, because ultraviolet rays are damaging to your DNA as well. One of the consequences of these sorts of things is that you do get an increase in cancers. And one of the reasons that can happen is because some of the things produced by the disaster don't just stay in the region of the disaster or the bomb, they get into the air and you can breathe them in. And those chemicals then irradiate the tissues inside your body. And if you include iodine in the equation, some of the species that get released are radioactive forms of iodine. They can be picked up by your thyroid gland, for example, in your neck, and they then irradiate your thyroid gland and they cause thyroid cancer. The other thing that should be borne in mind is when we have a nuclear disaster, just like a big volcanic eruption, you put enormous amounts of dust into the atmosphere, and this can have a climate changing effect. So we can still see the effect of very big eruptions in the past on the Earth's climate. When Krakatoa blew up in the 1800s over Indonesia way, the shock waves from that were heard and felt in Port Elizabeth, actually, not far from where I am.
Sure.
And that was sufficient to change the climate for 100 years. And the oceans are still a lower temperature and a smaller volume than they should be on the basis of Earth's temperatures because of the dust put into the atmosphere. A big nuclear holocaust could have equivalent climate changing effects. So it's not just radiation that stems from these things. There are other consequences as well.
Right. On the subject of UV rays, which you mentioned just now, we have a question asking, does the sun's UV ray differ in each country? For example, I find the sun's UV ray harsh in Cape Town and tend to burn after sunblock application. Yet when I was in Thailand, I found apart from the heat and humidity, I didn't burn, but managed to get a proper tan. Does the extremity differ in other countries?
Yeah, there are going to be differences. The sun puts out ultraviolet rays. Those ultraviolet rays include longer and shorter forms of ultraviolet. They hit the Earth's atmosphere, and between about 15 and 35 kilometers up, there is the ozone layer. Ozone is 3 oxygen atoms stuck together. And it's a very powerful molecule because it's very, very good at absorbing ultraviolet. Now, what that means, though, is if you are in the path of the UV without some ozone in the way, you're much more likely to get burned. If you live in, say, Australia or the southern tip of southern Africa, then because of the hole that we've made in the ozone layer, the ozone is thinner towards the lower latitudes over the poles than it is higher up near the equator because of the hole in the ozone layer. Therefore, your exposure to ultraviolet is higher than it would otherwise be because there's not that filtering effect of the UV. And the other thing to consider is if you go to an area which is more exposed, there's less shade, and you're in more direct sunlight, that will also have an effect as well, because the less atmosphere that the light has to come through, the less scattering there is of these rays and the less absorption of the rays into other atoms in the atmosphere, the more of them are going to hit you, so the more likely you are to get burned. So if you go to the top of a mountain, for example, that's going to make a difference. And also if you go sailing or go to the seaside, because the rays can all bounce up off of the water surface because they hit the water and they reflect off. And if you go skiing, same thing. The nice white reflective icy surface reflects the rays back at you. So you get a double dose. You get what arrives from above and you get the stuff reflected off the water or the ice.
Tell me, why do beans and sprouts make you pass gas?
The reason for this is that they are very rich in soluble fiber. Soluble fiber are forms of plant material which are indigestible to us. We lack the enzymes in our digestive juices that can break down these complicated molecules. They include things like raffinose and beta-glucans and things like that. When they then pass into your big bowel, the colon, this is a massive, massive zoo of bacteria. And these bacteria that live there, and there are billions and billions and billions of them, do have the metabolic knives and forks in their digestive juices to break down these chemicals that we don't have. So when we eat these things like Brussels sprouts, beans and so on, they end up in the bowel, and the chemicals that we can't digest, we feed to the bacteria. The bacteria can digest them, and one of the products of the digestion is gas, and this includes CO2, carbon dioxide, hydrogen sulfide, because there's a lot of sulfur compounds, also things that contain sulfur in those bean type things. They also make a bit of hydrogen, and you can also make some methane as well, according to the bacteria in your gut. So not only will it make you pass a lot of gas, you could also potentially set fire to it, but I wouldn't advise it.
Here's a voice note for you, Chris.
You were talking about the weather changing for 100 years after Krakatoa. Now, in those days, they didn't have jet airlines. If such an event had to happen today, and there was so much dust in the air that it changed the climate for 100 years, for how many years would aircraft not be allowed to fly? My name's Dave.
Hello, Dave. That's an interesting one. The answer to this is that there's a subtlety in this. When a volcano goes off, it does eject a lot of sulfur. And the sulfur forms sulfates high up in the atmosphere, and it's the sulfates which are very reflective, and they reflect solar radiation back into space. It's called an albedo effect. And that means if more energy is being reflected into space, there's less energy hitting the Earth's surface and the ocean surface, therefore temperatures fall. But one of the other things that a volcano can eject is dust particles, and particularly silica. In other words, glass and sand. And the reason that flights couldn't take off when, for instance, the volcano in Iceland blew up was because the amount of that material in the atmosphere would be totally destructive to airline engines. Luckily, that sort of material, and this happened also when Mount St. Helens blew up in America as well in the 1980s, I think that was, wasn't it? That you get this very big cloud of silica in the atmosphere, and you have to avoid flying into that because it will wreck your jet engines. It can just stop the engine because it forms glass inside the engine basically and rips the guts out of your jet engine. So you're not allowed to fly your engines through that sort of atmosphere. Luckily, that stuff doesn't stay airborne for that long. But the sulfate particles are really small, and they get very high up into the atmosphere, and they do remain airborne for a really long time. So the answer is it probably would have a short-term impact on jet travel, because if there's a massive volcano, you can't fly through the plume from that because it would rip the guts out of your jet engine. But the particles that do that don't stay resident in the atmosphere for very long. So it would only be a temporary short-term effect on jet travel, but the climate effects would be long-term.
We've got time for just a quick last one. Could a person survive in a falling lift if they jumped as it hits the ground?
Now, this is the classic one. We've all wondered this when we get into the lift, haven't we? And thought,
Right.
if the cable were to snap, what would happen? The answer is no. It would not help you to
Oof.
jump. You have to think about the physics of this. If you're accelerating downwards in the lift, in order for you to not hit the ground as hard as the lift is going to hit the ground with you in it when you get to the bottom, you've basically got to jump as hard as the lift is falling to completely
Yes.
negate the fall. If you could do that, you wouldn't need the lift anyway. So the answer is that no, this would be impossible.
Fantastic. Chris, it's always a pleasure and always so insightful. That's the Naked Scientist, Dr. Chris Smith. Enjoy your time in Durban in the balmy weather. And we look forward to chatting to you again next week.
Yeah, I'm looking forward to it. And I don't take much encouragement to get some enjoyment of the... I'll probably be sampling some local beverages, I'm sure, because I'm very fond of South African red. If anyone wants to send me a few bottles to try while I'm here.
Fantastic. We'll get your details. Have a
See
good
you
one,
later.
Chris.
Bye-bye.
All righty.